All right, let's open up to page 104. If I remember correctly, we still have to complete the last example. Is that right? On page 104? Well, maybe some of you did it on your own, but I think that we did not complete it as a class. Is that right?
No, we did not.
We did not. Okay. All right. So before we get there, though, I just want to give you a heads up, like what our weekly schedule is going to look like. We are going to start our last section of the unit today. We're going to take a look at one-to-one and inverse functions a little bit. Maybe we've heard those phrases before, maybe we haven't, but nonetheless, we're going to take a look at that today. Since it's the last section of the unit, we do have another partner quiz and a unit test coming up. So behind me is the anticipated schedule that I think is going to happen for this week. We're going to have our free response day on Wednesday in preparation for our partner quiz on Thursday, which means your review day will be Friday and unit test the following Monday, Tuesday. Does that make sense?
Everything we found up to 1.11.
1.11. Well, from the second half. Now, you still might see some things like above x-axis, below x-axis, but I think we're pretty good with that stuff. Okay? So, if our unit test is on Monday next week, what also happens on Monday? Homework. Okay, so homework from the unit will be due on Monday. And I'll let you know on Wednesday who your partners are for the quiz on Thursday. Now, the end of the quarter is on Friday, is that right? Okay, so notice how we will be able to get the quiz in before the end of the quarter. Depending on when guidance pulls your grades to run report cards, we may be able to fit the unit test on there as well. And I know some of you would like that opportunity. Some of you might be happy with what you have now and you don't want that to happen. So it's all going to depend on the timing. If it's close, I might be able to let you choose individually if you want the test on this quarter or next quarter. But again, we'll have to see how that pans out. Okay? But are we good with the schedule at least? What's happening when? Yes, Mrs. Bauer.
Yes.
Thank you. Okay. Let's take a look at page 104. So we were looking at this graphical example, and we had a table at the top. Part C is asking us to determine if this function notation is true, what would the graph look like from beginning to end? Okay, -6 to +6. So if you were to only graph the points in the table at the top, we can kind of see what that shape would look like. But notice how the points from the table only fill in half of the graph. They want us to go from -6 to +6. So we got to kind of figure out what's going on this left-hand side over here. How do you think we can use the right-hand side to help us fill in the left-hand side? Go to Emma.
Since the function is f of -x equals -f(x), we know that it's origin symmetry.
Origin symmetry. Okay, so that's our function notation for the origin symmetry, where you can flip it upside down and it would be exactly the same. What was our terminology that also signified origin? Yeah? Odd. Okay, origin symmetry, it's an odd function. So if we were to flip the graph upside down, it should look exactly the same. So if you actually tried that, okay, take a real good look of where it is now, and if you flip it upside down, this is what the remaining piece of the graph should look like. All right, so if we kind of go back, we need this, let's see, this line to go back down here, and then we'll have those portions. Kind of looks like a staircase. So if you flip it upside down, it should be exactly the same. If you wanted to use the point relationship, that's if we plugged in the opposite of x, we got out the opposite of y, you could use that also to help you find your ordered pairs. What was our other type of function, by the way? Instead of odd, it was Even, and what kind of symmetry did that signify? If it was even, yeah?
Why?
Y-axis symmetry. Good. Okay, so make sure we're good on that terminology. Are we good with the last one from that free response? Okay, I'll take the papers moving as a yes. All right, let's take a look on page 107. So the last section, kind of going to be simple concepts. We just got to make sure that we don't confuse these ideas or terms together. So we're going to revisit what it means to be a function and explore from there what some of these other vocabulary terms might mean. So way back from Algebra 1, what is your understanding of a function? Either how you can find one, what does it mean to be a function, anything. Do I need to go get Mr. Konjak or who was middle school? Mrs. Philo? Do I need to go get one of them to come over here? Wring your necks. They don't know what a function is. What's a function? Help. Not at all? Is there something you can do to test to see if a graph's a function? Oh my gosh, and the hands go up, yeah. Vertical line test. Okay, so if we have a graph, we can use the vertical line test to see if it's a function or not. Now the vertical line test is literally just that, a test to conclude some definition. So can you think about what the vertical line test is actually testing for? What are you trying to determine when you do that vertical line test? What's the relationship between the x variable and the y variable? What do you think, Seth? 1x for 1y, okay? So a function is a relationship between x and y such that each x has only one y. So when you do the vertical line tests, you're trying to see if that definition or relationship is true. 1x is related to 1y. If you had more than 1x related to the same y, your vertical line test would fail because you would touch your graph twice. So another way you can think about this definition of a function is that you have no repeating x's. So for example, if you had the point 2 comma negative 3 and you don't want to have any repeating x's, there should be no other point that has an x value of 2. Okay, so no other x value of 2. Could you have another y value of negative 3? Yeah, because the only thing a function tells us is that you don't have repeating x's. It doesn't specify about repeating y's. So you can have repeating y's. For instance, 2 comma negative 3 and 5 comma negative 3 are okay. Okay, that would pass the vertical line test. You're still only touching your graph once. So this is going to lead us into what a one-to-one function is called. So a regular, normal function that you are used to is a relationship between x and y such that each x has only one y. What do you think a one-to-one function is? A relationship between x and y such that each it's still x and y. There's a relationship between x and y such that each y has only one x. It's the flip statement. Okay, it's nothing too difficult. So we'll say a relationship between x and y such that each y has only 1x. So another way you could think about this definition is we have no y's repeating. So if you're already familiar with what a function is, flip the definition and you now know what a one-to-one function is. Okay, so they're two similar ideas but different analyses, okay, different connections here. So the previous example that we had, 2, -3 and 5, -3, even though those points are a function, they would not be a one-to-one function, because notice how you have those repeating y values. So what we're going to take a look at is different ways we can determine whether a table, a graph, or an equation is one-to-one. Okay, does every y have a single x associated with it? So when I say numerical, that normally means a table or points that you have. So we're going to try to take a look at a table of values to determine if it's actually one-to-one or not. So we're just going to jot down a little example so that this can make a little bit more sense. Let's say we have 1, 2, 3 for x's and then 4, 7, 0 for the y's. I'll zoom in a little bit. Is that table of values a function? Yes, because there aren't any repeating x's. Is that table of values a one-to-one function? Why? There's no repeating y's. Are you sure? You don't have to write this down. Okay, just visualize this. If we were to plot this, 1, 4, maybe right there, 2, 7, up there, 3, 0, right there. You don't know the rest of it, okay? So when you initially take a look at the table of values, and almost everyone in here said yes, it was one-to-one, you were assuming that those data points were not connected, right? You don't see this number 4 showing up anywhere else. You don't see the 7 showing up anywhere else. So if these points are not connected, then this would be one-to-one. But what if you connect them in order? Do you have a repeating y value somewhere? Yeah, anywhere between 4 and 7. Like if I pick 5, notice how that y value shows up twice, even though it's not necessarily written in the table. You see that? So tables can be tricky. Let's write this down. So it depends whether we're connected or not. Let's do connected versus not connected. So for this particular example, if the dots were connected, we would say it's not one-to-one because the y's repeat. However, if the dots were not connected, it was one-to-one because no y's repeat. It's a very tricky analysis. Somehow you have to know whether they connect or not. In some cases, okay, we'll see an example where it doesn't matter if we know if they're connected or not. Okay, but if we can determine if they're connected or not, that's definitely going to help us determine if it's one-to-one. Okay, so somehow they need to tell you whether they're connected, either by explicitly saying they're connected, but they can also say something like it's a continuous function, meaning you draw it without lifting up your pencil, aka you connect some dots. Okay, so there are some phrases out there that can signify the dots being connected. Okay, we have to be aware of those. So that's a table example. We're just looking for the y values. Are they connected? Are they not? What if we have a graph, okay, a picture? How do you think we can determine whether that graph is one-to-one, if it has any repeating y values? If the vertical line test was a way we determined graphically for a function, what can we use for one-to-one? Yeah.
Horizontal.
A horizontal line test. Good. So we're going to see if it passes the horizontal line test. Remember, a one-to-one function is literally the reverse statement of a function. So instead of a vertical line test, if we reverse it, it would be horizontal. That one's pretty simple. Analytically means we have some type of an equation to analyze, okay, by hand. So if we have an equation, maybe we can think about what that equation would look like if we were to graph it. And we've spent a lot of time this year talking about graphs of equations. For instance, if I give you a square root equation, do you know what a square root graph looks like? Isn't it that half of parabola? Okay, so if we have an equation, we got to think about what does the graph look like. Okay, think about the graph. And if you can picture the graph in your head, you can then use the horizontal line test to see if that would pass or not. So think about the graph and use horizontal line test. I know some of this might be over our heads right now, but it's going to make more sense when we eventually get to some examples. Okay, I just wanted to write down some strategies that we have. That way we kind of know what to do when those examples come. Okay, so another terminology that's going to be associated with this section is something called an inverse. Maybe you've heard this before, maybe you haven't. But by definition, an inverse function is defined to be the switching of the x and y variables. So it's a very similar concept to a one-to-one function, where it's the reverse statement of a function. We're simply going to switch the x's and y's. Now this is when I want you to put on your thinking caps for this last question. Okay, I'm curious if we can understand this. What property of a function, okay, if I were to give you a table, a graph, or an equation, okay, anything like that, what property would that piece of information must have in order for the inverse, if we were to switch the x's and y's, for that to also be a function? So if you were to start with a table that we know is a function, meaning no repeating x's, and you were to switch the variables, x's become y's, y's become x's, how can you tell if that new table of values is also a function? What do you think?
It has to be a one-to-one.
Why?
Because,
That's great. Why?
because if there's a repeating y value and you flip it, it will be a repeating x value, which makes it not a function.
Does that make sense? If we have repeating y's in the beginning table, and then you switch the x's and y's, those repeating y's become repeating x's, meaning our new inverse table is not a function, because it has repeating x's. Okay, so in order for an inverse to be a function, the original piece of information, graph, table, equation, whatever it is, must be one-to-one. And notice how we just talked about different ways to determine that. Okay, so we're going to say here, in order for an inverse to be a function, the original, what should we say? Instead of writing table, graph, equation, because that's a lot, the original information, maybe? The original information must be one-to-one. If it's not one-to-one, those repeating y's become repeating x's. Therefore, it's not a function. Okay? So we have this connection between all these terminologies. Function, one-to-one function, inverse. We're going to take a second and talk about different strategies again for us to determine an inverse piece of information, and then we'll get into some of those examples. So again, numerically meaning table, graphical meaning a graph, equation is analytical. okay, depending on which piece of information you have. So let's say we have a table of values. If you want to find the inverse, we simply switch the x's and y's. So we can say the x and y columns are switched. For a graph, though, you don't have x and y columns. You have x and y what? Points, coordinates. Okay, so the x and y points or coordinates are switched. Okay. What about an equation? You have you don't have x and y columns, you don't have x and y coordinates, you have x and y variables in the equation. Okay, so the x and y variables are switched. Now, for this analytical part, there's going to be a little bit more to it. Okay, simply or more than just switching. So after we switch the x and y variables, we're going to rewrite it a little bit. You are used to your entire high school career having a y equals equation, and that's what we're used to. So when you switch the variables, wouldn't it then become an x equals equation? So that might be a little bit foreign to us. We're not really sure what that means or why it looks that way. So after we switch the variables, we're going to solve for y. That way it's a little bit more eye-appealing to us, something we're more comfortable with. So that new equation we create is called the inverse equation. You can have an inverse table, you can have an inverse graph, you can have an inverse equation. Have we seen the notation for inverse before? Like the mathematical way to write or symbolize inverse? Have we seen the little f to the negative first notation? Yes, no, maybe somewhere in there. Okay, that just means inverse. So it's a special way to tell somebody, some other person, some other mathematician, that what you found is something special. Okay, it's the inverse equation to the beginning one that you started with. Okay, so we're going to use that notation in this section. Okay, so after all these strategies we wrote down, let's go ahead and try some of them. So taking a look at our first table here, can we determine if this table is 1 to 1? Do you see any repeating? What do you think, Emma?
Yes, because the 2 is repeating.
2 is repeating. So if we have repeating y values, is it 1 to 1? No. Okay. So not 1 to 1 because y's repeat, or at least one set of y's repeat. Now notice how it did not matter if the points were connected or not, because we automatically know based off the numbers that are given to us that it's not 1 to 1. So in this particular example, it doesn't matter if they're connected or not. So if we're not 1 to 1, what else do we know?
Can't be inversed.
Say it again?
Can't be inversed.
It can be inversed, but the inverse is what?
The inverse is not a function.
Not a function. Okay, so we'll say the inverse is not a function. All right, now we're actually going to find the inverse. And after we do it, we'll clearly be able to see why it's not a function. So we're going to create an inverse table, and we're going to switch the x and the y columns. So the previous, or the beginning x column should now be the y column, and the previous y column should now be the x column. And people say math is hard. I think you can do that, right? If you take a look at your inverse table, why is it not a function? Yes?
Because there are numbers repeating in the x values.
the x values repeat. So kind of similarly to what Eli said before, if we have repeating y's, they become repeating x's in the inverse. So we can clearly see why the inverse is not a function. All right, let's try another table. Is that table 1-to-1? Do we have any repeating y's? No, but we can't really tell because we don't know if they're connected or not. I don't think, I should have read the directions previously, but I don't think it says anything up there whether these points are connected or not. So we might have to analyze both cases. So if you just take a look at the table with the way it is, you are assuming the points are not connected. You're just looking at individual ordered pairs. So if we'll say not connected, then it's not 1-to-1, or it is 1-to-1 rather, because no y's repeat. Can we think about, though, if we were to connect all these dots, would there be a repeating y? Can you visualize these plotted in your head and kind of connect them as you go? Say it again.
There would be ones that would be.
How can you tell? Yeah.
It would go down from 6 to -2, and then it would go back up to -2, -1, so you already got an inverse there.
Okay, so if you go down and then you go up, okay, you have that change in direction. Notice how a y value would have to show up twice. You'd have to have the same height at some point. So if you can identify a change in direction, you know that a y value will be there twice. So if they are connected, okay, we'll say if connected, then it's not 1-to-1 because there would be y's that repeat. So unfortunately, if we cannot determine if it's 1-to-1 or not, we do not know if the inverse is a function or not. So we don't have that information available to us. But that doesn't mean we cannot find the inverse. Do you think we can simply switch the x and y columns? Yeah, that's our inverse. So we're going to do it. So x's become y's, y's become x's. All right, so there's our inverse table. We have no idea if it's a function or not, but we know it's there. Are we okay with table examples? Be careful, we got to think about if the points are connected. Let's take a look at graphs. How do you think we can determine if this graph is 1-to-1, if it has any repeating y values? Yeah. Horizontal line test. All right, so put your pencil down horizontally. If you trace it up and down, kind of like our range concept, notice how you'd only touch once. Okay, so we'll say, yes, it's 1-to-1 because it passes the horizontal line test. If it's 1-to-1, we also know that the inverse is a function. So let's see what this inverse graph might look like. Whatever it looks like, it should pass the vertical line test because we now know it's a function. So we're going to switch the x and y coordinates. For example, this first point in the corner, if its ordered pair is -5, 5, and you switched the x and the y, it would now become 5, -5. So this point, actually, the inverse point would land down here. Okay, we're going to go through all the other points and switch the values. So the next point, instead of -2, 1, we'd have 1, -2. The next point, instead of 2, -1, we'll have -1, 2. And the last point, instead of 4, -4, we'll have -4, 4. All right, so make sure you connect them in order. So it should look something like that. If you did a vertical line test, it would pass it. We said it should be a function, right? So it kind of checks out. Now, do you notice anything about these two graphs? Because we talked about symmetry in the last week quite a bit. Yeah.
They have origin symmetry because if you flip it, and then if you rotate it,
So you're saying if we rotate the black one, would it become the red one? Is that what you're saying?
yeah, like what?
Let's see. So if we rotate it, would the black one become the red one? No, not exactly. It's close to origin, but not quite. Is there another one? You see it?
Did the axis and y change?
So what type of symmetry was that one?
At y equals x.
The diagonal symmetry. Okay, remember that was our special that was our special point for the diagonal symmetry where we had y comma x. Okay, it's the concept of an inverse where we're switching the x's and the y's. So if we have this diagonal symmetry between an inverse and original, if I can spell, diagonal symmetry, this should happen every time we have an inverse graph. Okay, it's related to the original through this folding diagonally symmetry. All right, so y equals x. Let's try another graph one. Is the next graph 1 to 1?
No.
No. Okay, so no, because it will say it fails the horizontal line test. So if it's not 1 to 1, we know the inverse is not a function. So when we actually find the inverse graph, it should fail the vertical line test. So let's see what that looks like. We're going to switch the x and y coordinates. So -4, 4 becomes 4, -4. -2, 0 becomes 0, -2. 1, 3 becomes 3, 1. And 5, -4 becomes -4, 5. Okay, connect them in order. There's our inverse. Not a function, right? Fails the vertical line test. We doing okay? Do you guys think you can try the next graph on your own? On page 109? Determine if it's 1 to 1. That should tell you about the inverse, whether it's a function or not. And then I actually want you to find the inverse picture. Okay, find the inverse graph. See how you do. How do we do? Pretty good. Can we see the diagonal symmetry? If you were to fold it corner to corner, wouldn't the black one line up with the inverse one? Okay, I think that's another good visual. All right, let's try an equation. We might just get the one today, but that's okay. So for an equation, because we already did tables, we already did graphs, for an equation, we got to think about in our heads what would the graph look like so we can turn it into a picture and then see if the horizontal line test would pass or would it fail. So can we determine what graph this function would have? Can you tell? What do you think, Seth? Say it again. How'd you know? The squared. All right, so this is cluing us into a quadratic function. So it has a parabola. All right, so we'll say f of x is a parabola graph. Would a parabola pass the horizontal line test? No, because it would touch twice. All right, so f of x is a parabola graph, and the horizontal line test fails. So we're not one-to-one. What do we know about the inverse? Yeah, not a function. All right, so the inverse, not a function. Now, just because the inverse is not a function doesn't mean we can't figure out what the inverse would be or what it would look like. So we're going to actually figure out what the inverse equation would be. So we figured out inverse graphs, we figured out inverse tables, now we can do inverse equations. So just like everything else that we've been doing, we're going to switch the x and y variables. Now, f of x and y mean the same thing. So if we switch x's and y's, this would actually look like x equals y minus 3 squared minus 2. But like I said before, we're not used to seeing x equals equations, so that's when we're going to solve for y. That way it's a little bit more comfortable for us. So how do you feel like getting that y variable all by itself? Yes, Lucas? Add the 2. All right, so x plus 2. Can we keep going? Yeah.
Square root both sides.
Okay, so when you square root both sides, what else do we need? Have we seen the plus or minus before? Yeah, whenever you square root both sides, we need a plus or minus. So this would be plus or minus the square root of x plus 2, and that would be y minus 3 we're left with on the right-hand side. Lastly, yeah? Add the 3 over. Okay, so we'll have plus or minus the square root of x plus 2, and then after that, we got to add the 3. Okay. There's our equation for the inverse. Now, if you were to graph this, you would have a positive square root, but also a negative square root. So if you think about what that would look like, a positive square root looks like this. A negative square root, if we flip it, looks like this. That definitely would not pass the vertical line test, right? Because we said the inverse should not be a function. So here is our inverse. Okay, do me a favor. Instead of y, let's label that f to the negative first. Okay, that's our notation for inverse. We'll check out the other 2 examples tomorrow. Maybe you want to get a heads up on them and try them yourself, okay? But we'll see what these inverse functions look like later.